So we're continuing exercise 20.41. We've finished doing up to D at this point. So here we have E. When you look at E, we don't just have an alkane this time. We have an alkene, and that means that a lot of possibilities are open to us. Having those extra electrons in that pi bond, especially since the pi bond is so easy to break, really opens up a lot of possibilities. Electrons are like molecular glue that hold the nuclei of atoms together. And so wherever you have extra electrons, like with those in that pi bond there, a lot of chemistry is open to you. Specifically, there would be the around 10 or 11 addition reactions that you learned in the addition reactions of alkene chapter in Organic Chemistry 1. So that doesn't narrow down for us really what we need to do. But if we look at our product, we might be able to go backwards, right? Instead of, you can think of synthesis going forwards, and if you get stuck that way, like we just did, you can look at the product and think, how can I go backwards? That's called retrosynthesis. Now in this case, we see a feature that's very distinctive. We see a nitrogen double bonded to an oxygen. That is an imine. That's something we've only learned about in this chapter. And the way that we learn to make an imine is to take a primary amine, so primary amine, that's an amine that's only bonded to one carbon chain, so it'll have two hydrogens. And in this case, the carbon chain, you can put the carbon chain as whatever is bonded, single bonded to the amine. So for example here, we just have this isopropyl group. The two bonds to the hydrogens are what is ultimately going to get replaced with the double bond to that carbon. So that's one thing you need, a primary amine, and the other thing you need is an aldehyde or a ketone, a carbonyl. Now here, our carbonyl is going to be the rest of this molecule. So we'd have the ring, carbon, and double bond, but instead of the nitrogen, it'll be to an oxygen. So if we mix those two together, in this case an aldehyde with a primary amine, it will give us our imine. Okay, so we know that we can, if we had these pieces, we could get this product. Now the primary amine, that's fine. We can order that, we can make that some other way. That'll be our reagent. The carbon chain whose story we're following is the one with the ring. So how could we turn this alkene into this aldehyde? Right, notice this is an aldehyde because there's a hydrogen here. Because that carbon only had 3 bonds written in explicitly, and the only bonds that can be there without being written explicitly are bonds to hydrogen. Okay, well, when you look at this, when you compare our original starting material to the aldehyde that we need, what you'll notice is that an element has been added on to the molecule. There's no difference in the number of carbons. There's still the same number of carbons, but you've added an element onto the molecule, and that element is an oxygen. So how do you add oxygens onto alkenes? You do hydration. Now there are 2 ways you could do this hydration. Let me move this over so that this will come back to us later. But if you want to do a hydration, you have 2 ways. You could do a Markovnikov addition of H and OH. So that the recipe for that is acid catalyzed hydration. You use sulfuric acid and water. And in that case, the OH would end up adding to the carbon in the double bond that is more substituted. So notice the carbon here, that carbon is bonded to 1, 2, 3 other carbons, so it is tertiary. And the carbon on the other side is only bonded to 1 other carbon, so it is primary. So Markovnikov addition means the OH goes to the more substituted carbon. That means the OH would go here. So that's one possibility. The other possibility, if you want to add H and OH, is you could do an anti-Markovnikov addition. And that's hydroboration oxidation. So first you add hydrogen and boron with BH3, that's stabilized by tetrahydrofuran, THF. And the second step is to replace the boron with an oxygen, so it's oxidation. So overall it's hydroboration, and then this next step, oxidation. And that also adds the H and the OH, but it does so in an anti-Markovnikov way. So the OH goes to the less substituted carbon. Here that's the primary one. The OH goes here, and the H goes to the other side. So those are our two options. And if we think about the molecule that we want, you could see that we really want the anti-Markovnikov product, because that gives us the oxygen on the correct carbon. So we will not do this Markovnikov addition in this example, but you should be prepared to be able to do a Markovnikov addition, if necessary, in a synthesis. I'm going to get rid of this hydrogen because it's implied in the skeletal structure. Now if we compare this alcohol with the ketone that we need to create the imine, you'll notice the only difference between those two is an oxidation. This has one bond to the oxygen, this has two. Now you have to be a little careful because this alcohol, the carbon that has this OH on it, is primary. It's only bonded to one other carbon. And so you have to use the weak oxidizing agent that we discussed. And that is PCC. That's pyridinium chlorochromate. Pyridine is kind of like benzene, but it has a nitrogen in it. So the lone pair there is not involved in the aromaticity, so it can act as a base, steal an H+, and then you would have this. So that's pyridinium, because it's an ion. So that's pyridinium. That's what the P is standing for. The second C is standing for a chromate. You have this chromium molecule. And you replace one of the chromiums that you're used to with a chlorine, and that's what the C is talking about. So this pyridinium, the positive charge on it, is stabilizing the negative charge in the chlorochromate, and that weakens the power of the chromium compound to do the oxidation. Now we won't go through the whole mechanism for that, which is pretty long and a little bit complicated, but you could see how the positive charge on the pyridinium, the P in the PCC, stabilizes the chlorochromate, the CC, and so it's a weak oxidizing agent, which means that it'll take a primary alcohol like we have here and only bring it to an aldehyde. It won't take it all the way to a carboxylic acid. So what you want to remember, the big takeaway message, is if you have a primary alcohol and you treat it with PCC, you get an aldehyde. That's the only way to form an aldehyde from an alcohol. Well, once you have your aldehyde, you just have to treat it with the primary amine that we talked about, and that gives us our product. We end up getting the imine. The double bond to the oxygen gets replaced with the double bond to the nitrogen, which now still has that carbon chain, but neither of the hydrogens. So we get sort of the nitrogen version of our carbonyl. So overall, the steps for this, if you were just listing the answer, the sort of recipes you had to use to cook up this thing, you'd want to do hydroboration oxidation. So add boron and hydrogen, hydroboration, in the presence of THF, tetrahydrofuran. Replace the boron with an oxygen, so that's oxidation. You do that with sodium hydroxide, hydrogen peroxide. So that recipe there will turn this double bond into a primary alcohol. Then we use PCC to take the primary alcohol to the aldehyde, and last we treat that with a primary amine, whose carbon chain is based on the carbon chain that we need, that reacts with the aldehyde to create an imine. And so these are the recipes that we would need to make that reaction happen. What gave everything away here was the presence of the imine. That was the unique feature that told us, okay, we need a primary amine and an aldehyde. Okay, for F. Now in F, you'll notice that you have a benzene ring. You start with a benzene ring. So instantly, you should be thinking, okay, aromatic substitution reactions. That's probably what we're going to be dealing with here. The branches that we're adding onto the benzene ring are bromine and some sort of a weird carbon chain. Now let's think about these separately. How do you add a bromine onto a benzene ring? Well, it's Br2 but that by itself is not a good enough electrophile to react with this very weak nucleophile. To turn it into a good electrophile, we use a metal catalyst like FeBr3, or you could also use AlBr3. Now, if we look at the other thing we want to add onto this benzene ring, and we're just thinking about the recipe, you'll notice we have a new carbon-to-carbon bond between this chain and the ring. And that's a sign that we have to do Friedel-Crafts. We could either do Friedel-Crafts alkylation or Friedel-Crafts acylation. Remember, the difference is that in Friedel-Crafts alkylation, you take a carbon chain that does not have any double bond to an oxygen, you combine it with a metal catalyst, and that ends up adding that chain onto the carbon branch. And that looks kind of similar. If you choose the right carbon chain, you can make it look kind of similar to this. You could definitely do that and get the reaction done, but it might be a little bit more efficient if you do the Friedel-Crafts acylation. Remember so this is an alkylation. If you're doing the Friedel-Crafts acylation, that means you take the benzene ring and you treat it with an acyl group. That's a carbon to oxygen double bond and then some sort of a carbon chain. And you still need the metal catalyst to get that to work. So that adds this this acyl group onto that ring. Now technically, both of these can be turned into this branch. It happens to be a little easier, or rather faster in the case of the acylation than the alkylation. Let's forget the bromine for a second. We'll come back to that. We'll think about the kinks with that. Let's just look at how we could turn each of these branches, these carbon branches, into the branch that we want. Let's start with alkylation. We need to add a double bond here. To create a double bond, first you would need a leaving group. You create double bonds doing elimination, and you do elimination when you have a base in a leaving group. So to get a leaving group, we can use NBS and light, or heat. Since it's the benzylic position, which is really reactive, you could use heat instead of light. Heat is in this case, more gentle than the light would be. So because it's so reactive, you can have gentler reaction conditions. That'll put a bromine on the benzylic position. And then you can use a base. Now in this case, we want the double bond to be the less substituted double bond. Let's draw the two possibilities. You could either have a double bond form going up, that's what we want, or you could have it form going to the right, which is what you don't want. Notice that this one is less substituted. The two atoms here are only bonded to two carbons going away from the ring, so that's the Hofmann product, as we discussed in a previous video. This one here, the carbons have 1, 2, 3 carbons coming off of the ring, so that's tri-substituted. It's more substituted, so it's the Zaitsev product. So Hofmann is less substituted, Zaitsev is more substituted. We, in this example, would want the Hofmann product. And you get the Hofmann product by using a bulky base. Because as you can see, the hydrogen here that you'd be stealing is much less crowded than the hydrogen here. A bulky base will reach this better, and the bulky base you'd want to be familiar with is potassium tert butoxide. So I'm going through this really fast because we've talked about it in more detail in previous videos. So you'd want to use a bulky base like potassium tert butoxide and not a skinny base like sodium hydroxide, sodium methoxide, or sodium ethoxide. Okay, so there are two steps here that you can do in order to turn. You can so you can either do this if you're trying to get this branch. You could do a Friedel-Crafts alkylation followed by NBS and heat, and then a potassium tert butoxide. Or you could do Friedel-Crafts acylation. And if you notice, if you compare, we just need to turn this oxygen into a CH2. You could actually do that in one step, right? That would be forming a new carbon-to-carbon bond here, and there are very few ways to do that. If you want to form a carbon-to-carbon double bond, that's a sign that you'd want to do the Wittig reaction. So we have our ketone. All we would need is the carbon that we want to replace the oxygen with, CH2. That's what's up here. And have that double bonded to a phosphorus bonded to 3 benzene rings. And that, in one step, would give us what we want. So Friedel-Crafts acylation, I think, is the easier way to go here. You just follow that up with a Wittig reagent. But you could theoretically do the Friedel-Crafts alkylation, and then the radical bromination, and then the elimination reaction with the bulky base. So notice there are many ways you can get these reactions done. There's more than one correct answer for these synthesis problems. So long as what you give me is a correct answer, I will not take points off, even if it's not the most efficient one. It's completely fine. I just want to make sure you could get from point A to point B somehow. Now, okay. Now, in this case, I'm just going to go with the Friedel-Crafts acylation in the Wittig reaction because it's shorter and more efficient. So we'll take that away. Now, up until this point, we've looked at our 2 branches, and we've come up with the recipes that we need in order to add the 2 branches on. However, you'll remember that when you add things onto the benzene ring, you have to think about whether each branch you add is ortho-para-directing or meta-directing. Remember that the halogens are weak deactivators, and they are ortho-para-directing. Let me do this in another color. Here, we have 2 different products. We have the acyl group on the benzene ring. Remember, if you have a pi bond to an electronegative atom on the benzylic position, that's moderately deactivating and meta-directing. And finally, we just have an alkyl group. Alkyl groups are weakly activating and ortho-para-directing. Well, if we look at how we want these, we want the bromine and the carbon chain to be meta to each other, 1,3, right? If you have 2 things on a benzene ring and they're 1,2, they're right next to each other, that's ortho. If they're 1,3, it's meta. If they're 1,4, it's para. We want them to be meta. And the only meta director is this here. So the order that you have to do this in is first, you have to take your benzene ring and add the acyl chloride and the metal catalyst. That puts that acyl group onto the benzene ring. Now we have a meta director. So now we're going to add the bromine, so that'll add on the meta position. So that gives us the bromine on the meta position. And finally, we can do the Wittig we can use the Wittig reagent, this carbon double bonded to the phosphorus. That carbon could theoretically have any carbon chains on it. I'm putting hydrogens here because that's what it has above. And that would give us our final product. It's very important that the reactions are done in that order. So first, the acyl chloride with AlCl3. Second, the bromine with FeBr3. And third, the Wittig reagent. Notice if you do them in any other order, the reaction won't work. For example, if you try to take the benzene ring and you try to treat it with the bromine first, so Br2, FeBr3, you would end up with the bromine. Let's say, I mean, all these positions are symmetrical, so we'll put it there. But bromine is an ortho-para-director. So if you then try to do the Friedel-Crafts acylation, if you try to have the acyl chloride with aluminum chloride, it will add ortho and it will add para, but it will not add meta. So you'd have the bromine, you would have that as one product, and you'd also have, so this is the ortho product, you'd also have the para product. But neither of those are what you want, which is the meta product. So you can't put the bromine on first. So this is a crucial order. It's not a long synthesis, which is good. That means it'll be more efficient, but it does require some thought. Anytime you're trying to add things to benzene, first write down the syntheses you need in order to get those branches individually. But then think about what type of directors they are, and so what type of order you need to do the reaction in. Okay, I'm going to do G really quickly because this one really borrows from the next chapter, the chapter on carboxylic acids, so this one wouldn't be emphasized on this next test. Nonetheless, just in case you're interested, or if you want a little bit of extra practice, or if you want a sneak preview of what we'll do in the next chapter, we can combine that with what we learned in this chapter in exercise G here. When you look at this, so I'm going to do this fast because it's not particularly relevant for this test, but it's extra. So if you look at what we have, you'll notice that our product is an acetal. You have a carbon bonded to two ethers, the same carbon, so that's an acetal. And if you look at our reagent, we see the same carbon has a carbonyl. So instantly we know this is going to be acetal formation. To make an acetal, you need a carbonyl and you need two equivalents of an alcohol. We don't have an alcohol here. We have a different functional group. We have a carbon double bonded to an oxygen, single bonded to an ether. Now that's a functional group called an ester. That we'll learn about in the next chapter, and that's why this question won't be emphasized on this test, because esters really aren't a part of this chapter. The one thing you can do with esters that should make kind of sense is that you can use a reducing agent like lithium aluminum hydride, and that will turn them into alcohols. So if we use lithium aluminum hydride, and that is a reagent you should definitely know for this test, sometimes you may see that also written as LAH. It's the same thing. I prefer this top one myself because you can see what's in the reagent. If you treat that with lithium aluminum hydride, it will reduce those esters to alcohols. The problem is that it will also reduce, of course, the ketone to an alcohol. We've covered that in this chapter. That should seem familiar. And this will not give you an acetal. In order to have an acetal, you need the ketone to stay a ketone. In other words, we have to protect this ketone somehow before we do this reduction. And that we can do by actually forming another acetal. Ketones can form acetals, but esters cannot. And again, we'll discuss the reactivity of esters in the next chapter. But what we can do is first treat this with a diol. Now if we do that with an acid catalyst, and if we remove water, that'll help push the equilibrium forward, that will give us an acetal. Now that won't do anything to the esters. Esters do not react with alcohols to form acetals. What it will do is turn the ketone into an acetal, or these two carbons here. Now, this is protected. That carbon will not react with the reducing agent. And when you treat it with lithium aluminum hydride, you end up still having that acetal in the middle there. So you reduce the esters, but what was the ketone isn't affected. Well, remember that the acetal formation is an equilibrium. It goes forward and backward. And so once you've done this reaction, you can take the acetal off by adding water. Now technically, after you do these reductions, these oxygens have a full negative charge, because the hydrogen attacks as a nucleophile and kicks the carbonyl carbon, the electrons in the pi bond, onto the oxygen, so you get the negative charge, kind of like with when Grignard reagents attack. So if you treat this with excess water, or even better, excess H3O plus water, that will put hydrogens on this molecule. And in addition to that, it will push the equilibrium for the acetal toward the ketone. And so that will turn in to the ketone. And now you have the recipe that you need to form the acetal. You really just need to add a little bit of catalytic acid and remove some water. So this is minus water. So you heat the solution up so the water's evaporating. And that will turn this ketone and the two alcohols into an acetal. Now notice there are going to be two carbons and then an oxygen. So 1, 2, and then an oxygen, and then it's bonded to the carbon that was in the ketone. And the same with the other one. 2 carbons and an oxygen. So 1, 2, and then an oxygen, and then it's bonded to the ketone, the carbonyl carbon. And you'll see that that's the product that they gave us. So this synthesis involves esters, which is why it's not going to be emphasized on this test. But things that are relevant to this chapter are the use of the formation of acetals, putting them on a molecule, and using water to take them off. And we also saw in this chapter using lithium aluminum hydride as a hydrogen nucleophile to reduce carbonyl compounds, to turn carbonyls into alcohols. So that helps maybe some review for this chapter. And otherwise, the one cool thing that you see here that's really clever and good to know is that you can use diols to protect ketones. So if you have a reagent that's going to react with a whole bunch of stuff, and you want the ketones to stay in their place, you can use this diol to protect it, do the crazy, strange, violent reaction, and then take the diol off just by removing the acetal, by adding some aqueous acid. So when you add a diol like that to protect a ketone, it's called a protecting group. And that's a whole field of organic chemistry, is using protecting groups like that, so that a functional group that you have won't get destroyed when you do a violent procedure to make something else in a molecule react. It becomes more and more important as you create bigger and bigger molecules, because you don't want the stuff you already created in one place to get destroyed when you do a reaction in a different place. So that's a little extra with G. And hopefully these last few syntheses shed some light on some other ways that you can do reactions with aldehydes and ketones, some synthesis with aldehydes and ketones.